All right, thanks everybody for coming. This is the last in the series of 6 lectures we've had about the Bootstrap. Although this is a bit of a standalone, whereas previous lectures were kind of going through the nitty-gritty of how Bootstrap works, and in particular allowing people to figure out how to compute an island for the IC model using code. Here, we're just going to talk about a broader perspective of what I think are kind of the most significant results of Conformal Bootstrap to date, as well as future things that people should work on in the future, hopefully inspired by this class. All right, so let's jump right in. So as general introduction, Conformal Bootstrap is currently the most powerful / general non-perturbative method of studying conformal field theories in D greater than or equal to 2. And so it's already been used to solve long-standing questions in condensed matter systems, which usually means non-supersymmetric CFT in 3 dimensions. Usually that's what people mean by condensed matter. It's also been used to study quantum gravity via the AD-CFT correspondence. So there's been a lot of good results so far, but there's much more to do. And I would say many of the biggest questions remain open, and both technical and conceptual progress is needed. And so that's why kind of the purpose of these classes is not to kind of give you an overview of a subject which has been done. It's a subject which is expanding. I would even say at an early stage, and there's a lot more to do. So hopefully people will kind of use the tools they learn in the class to accomplish some of these goals. All right, so the outline of this last talk is first we're going to discuss condensed matter results in 3D, i.e. 2 + 1 dimensions. So in particular, we're going to discuss the critical ON model, as well as the critical gross nouveau U power model. And then we're going to talk about some future directions for condensed matter. In particular, I think the family of theories known as QCD3 is of interest, as I'll describe. Then we're going to transition to quantum gravity applications. So we're going to talk about results in AD-CFT in various dimensions. So for instance, n = 4 super mils in 4D, maybe gem theory in 3D. And in terms of future directions, I'll focus on one particularly interesting mysterious theory, which is the 62,0 theory. And then finally, I'll conclude with kind of general future directions, not specifically about an application, but just general things that could be developed using Bootstrap. Okay, so let's begin with probably the simplest CFT, which is the critical ON model. So this is just n real scalar fields phi I with an ON global symmetry. So you can write down a Lagrangian for this theory, which is just a kinetic term plus a phi to the 4 potential. And usually we're interested in discussing this theory in 3D, because in 4D it's just a free theory and 2D doesn't exist. So 3D is an interesting case. It's strongly coupled in 3D, so you can write down this Lagrangian, but you can't really do much with it. The coupling is big. And so prior to the Bootstrap, the way people would study this is either you could use perturbative methods, such as making n become big. We're doing a Four-man epsilon expansion around 4D, where it's a free theory. But of course, these aren't really rigorous when you look at finite n or exactly in 3D, because these are kind of asymptotic expansions, and you're kind of doing a non-rigorous extrapolation to the region of interest. Other approaches people have used is lattice results. And these are available for all n in principle, in particular low n. And so these are some results that we'll be able to compare our Bootstrap results to. So at least for the family of critical ON models, you could say that even prior to the Bootstrap, there was lattice methods which gave us a decent understanding. Although, as you'll see, for some questions you need extremely precise predictions, and for that, Bootstrap actually does a little bit better than lattice. Okay, so just to kind of briefly review the Bootstrap, for maybe those who missed some previous lectures. The inputs to the Bootstrap do not involve the Lagrangian. So all they involve is conformal symmetry, unitarity, the global symmetry, in this case is ON, and the number of relevant operators in each representation. So in particular for the critical ON model, we kind of define the model because it's a critical theory, as opposed to tri-critical theory, it's basically defined to have one relevant singlet. You can see that's part of the definition of the critical ON model, as opposed to some putative other model. And so these are the only inputs. So we're not using the Lagrangian, we're not using any other, intuition from experiment or anything else. This is basically how we're defining the theory. Okay, so we can start with the simplest example of this class of theories, which is when n = 1. That's just Ising model, because the global symmetry is Z2. So the relevant operators is there's one relevant Z2 even, one relevant Z2 odd. We call them epsilon and sigma. This, of course, has many, experimental applications, describes phase transitions between water and vapor, quantum magnets, etc. Even bird clocks, as I just described by the Z2 model. So this is a famous model. So of course, it's been studied, over the years many times. So particular lattice studies from 2010, which computed critical exponents to very high precision. But a question you could ask is that because this is the simplest CFT, probably the simplest quantum field theory, for this, special, incredibly simple theory, can we just compute everything? Can we just like completely solve the theory? It's like, I think it's like a natural question to ask. I mean, after all, in 2 dimensions, people have completely solved the 2D IC model. In that case, it's a minimal model. And so like, could one hope to do the same thing in 3D? So this was kind of the first classic result of the Bootstrap, which kind of made people interested in it, is that back in 2014, precise islands were found in the space of scaling dimensions of these 2 relevant operators, sigma and epsilon. And these were found by considering 4-point functions of mixed correlators between sigma and epsilon. So since these original islands were found, they were already pretty small, but since then, the islands have been shrunk even further, basically by just improving the precision of the Bootstrap, as well as scanning over OP coefficients that appear in this 4-point function. And so as discussed in the previous lectures, this OPE scan really allows you to kind of reduce the allowed region. So to give kind of an idea of how these bounds have improved, there's this video which was made by David Simmons-Duffin, which I'll play now. So that eerie sound hopefully gives you an idea of how otherworldly it is. The fact that you can get such an incredibly small island for the IC model, because as you see, it's significantly smaller than Monte Carlo. I mean, like Monte Carlo is much bigger than the size of this island. And this video was also made something like 5 years ago. So I think since then the island's become even smaller. I mean, you could ask this kind of a general question: will the island just shrink to a point? I doubt it, but like incredibly small.
By shrinking the point, you mean that there is some analytic solution of this model?
In particular, like you could ask a question just by doing Bootstrap of mixed correlates with sigma and epsilon. Could you hope that you could actually literally just get an answer? And like so that I would be a little surprised. I think probably in principle to really get to a point, you would probably have to look at infinite correlation functions. But what's impressive is that by just looking at correlation functions of sigma and epsilon, you could get an incredibly small. Which for any experimental purpose is of course enough. Although like this is more kind of like a proof of principle. So like, can you actually solve a CFT? Like at this point, we're not doing this to learn more about experiments because we're not going to be going to like 20 digits in any experiment in the near future. Although I mean, there are reasons why you would want to know CFT data to high accuracy. Because sometimes you have theories which aren't the IC model, but they're near the IC model. And so if you want to do conformal perturbation theory, then it is very useful to know CFT data to high accuracy. So it's not a completely academic exercise.
What is an example? What is
Well, like I guess like say you want to say like long range IC model. So like there's been studies where people use conformal perturbation theory. This is people by Zohar from Rogotsky and David Simmons-Duffin, where they use basically CFT data for the IC model in 3D, and they use the fact that I guess like you expect that this long range IC model is like not that far from the IC model through conformal perturbation.
shouldn't it follow directly to the IC model?
So shouldn't what?
Shouldn't it follow directly to
No, it's a different theory. So there's something called the long range IC model. It's a different theory than the conventional IC model. And you can study it by doing conformal perturbation theory from that.
But it's not a local system.
It's not local.
It doesn't have stress energy tensor.
Yeah.
Okay.
So this gives the results for the IC model. Another interesting thing you learn from the Bootstrap, like when you bootstrap an island, you're not just learning about the specific operators in that island. In principle, if you find a solution to the Bootstrap, even numerically, you can read off all the CFT data that appear in these 4-point functions. So particularly for the IC model, this is pretty much every operator, with the exception of parity odd operators, because they would not appear in these 4 functions. Next, forgetting about the parity odd guys. So here is a table which is showing this nice paper from David Simmons-Duffin from 2017, how you could read off a huge range of operators. So like the x-axis is spin, the y-axis is twist, which is just dimension minus spin. The size of these circles is how accurately he's been able to estimate these operators. So as you see, usually low twist operators you can get pretty accurately, like the lowest few twists. As the twist gets bigger, you need more and more accuracy. This shouldn't be so surprising for those who attended previous lectures, because we learned that the tail of the block expansion becomes exponentially small, and so that means kind of like the Bootstrap naturally only sees low-lying operators. In a sense, that's how it works. Because if it's not every single operator, how would you ever be able to do a truncation to put it on a computer? So it's both a blessing and a curse, the fact that you don't see these high-dimension operators. But still, nonetheless, you're able to see the lowest few operators, and one could imagine that just by pushing precision higher and higher, maybe you could see enough low-lying operators for any question you would be reasonably be interested in. Okay, so moving on from the icing model, we can now talk about the O2 model. So now n equals 2. So in this case, the relevant operators, you have one relevant singlet, one relevant charge 1, and one relevant charge 2. And so this theory describes phase transitions in many systems, for instance, superfluid helium. So if you're studying superfluid helium, it turns out that, like, I guess by varying the parameters in your experimental apparatus, you can actually get like a line of second order phase transitions. I mean, the line all corresponds to the same theory, but it's just in the parameters you're measuring. It turns out there's actually like a line where you all get to the same theory. And so this is something people actually study experimentally. In fact, it turns out that I think this might be the second order phase transition which you can most accurately measure. This is what I'm told. And so this is also a very well-known theory. So of course it's been studied by the lattice to very high precision. So here are some results from 2019. But despite all these very accurate results, there was still an outstanding question, which is that people did an experimental study of superfluid helium on the Columbia Space Shuttle back in 1992. And so they measured critical exponents. The reason why they did it on the Space Shuttle is because the experiments are so accurate on Earth that it started being the case that gravity was making an error. Where it's basically you're measuring some sample, and because gravity is slightly different in one part of the sample versus another part of the sample, that made some kind of error. And so that's why they wanted to go to space where there's no gravity, so that you would avoid this error, which kind of shows how accurate the experiment is. I mean, for condensed matter people, this is like insane accuracy. That's like, this is particle accelerators. Like usually getting a couple sigma accuracy in condensed matter, you get a Nobel Prize for that. Anyway, and yet in this case, they had an 8 sigma discrepancy from these lattice results. So this was very surprising. Because usually we trust the lattice, and yet we're getting a completely different answer than what this incredibly accurate experiment on the space shuttle was done. And by very smart people at Stanford. I thought it was at Stanford. No, the Columbia is the name of the shuttle.
Okay.
Yeah, it's the name of the shuttle, but not the university. Should have called the Stanford shuttle. Anyway, so in a paper from a couple years ago, I studied this theory with various collaborators. Just by doing mixed correlators of the various relevant operators, scanning over B coefficients. And we got this very small island shown in blue here. And first of all, the green is Monte Carlo. And so you could see that it overlaps to some extent with Monte Carlo, showing that Monte Carlo, was not crazy. They were in the right direction, although our island is smaller. The brown is the experimental prediction. So the brown is just planes because they didn't measure all 3 critical exponents. They only measured 2 of them. So that's why it's a plane. And so this basically shows that there was some error in this experimental analysis. Because like we rigorously show that this O2-Wilson-Fisher fixed point has to be where Monte Carlo says, it cannot be where the experiment says. So that, of course, it asks the question of like, what mistake does experimentalists make? Well, I'm not an experimentalist, I don't know. But these are very sensitive measurements. And so, I mean, this error, it's 8 sigma, but like usually condensed matter experiments are not that precise. So as you see, like, maybe they claim it's something like, I don't know, what's the axis here? Say they claim it's 1.509, we're claiming 1.511. It's not unimaginable you would make such an error. It's the same magnitude.
Could it be that there is some different cause by CFT?
Okay, so that I think is less likely though, because it's like, the definition of a critical theory is that you only have to tune one parameter to get there, right? And so like if there was really different CFT, there'd have to be another CFT with O2 symmetry and only one relevant operator. And that's basically ruled out by the bootstrap because we get this island. I mean, like the island, it's not saying everything is disallowed outside the island. There's always like an allowed region far away, but that would be really far away. And that would almost certainly exclude the values. So I think the simplest explanation is that like there's just probably some systematic error with their analysis. So they should send up another space shuttle. Maybe the NYU space shuttle. Okay, so this is kind of an example of like a nice thing you actually learned from precision bootstrap. Because like as a cynic, you might have said like, oh, these ON models, we studied them to death back in the 70s, like, who cares? But this was like a real outstanding question with experimental implications. You needed a precision study, and it's only because of that precision study that you can answer this question.
If you are really a cynic, you can still say who cares.
Well, cynics can say who cares about it. But at least this is an example of what we're supposed to be doing as physicists. We have a question about nature, we measure it, and then we try to get a prediction which matches what we measure. Okay, so now we can move on to the O3 model. So in this case, there's certainly a relevant singlet, isospin 1, isospin 2, isospin 3, and there might be a relevant rank 4 operator. So this would just be if you have like your field phi, there might be an operator for I, phi j, phi k, phi l, which is relevant. Now, why do I say maybe and why is this important? So if this rank 4 operator is irrelevant, then the O3 model would describe phase transitions for classical Heisenberg magnets. The idea of a classical Heisenberg magnet is like some kind of lattice where at each point you have something which can rotate in 3 spatial dimensions. That's why it has an O3 symmetry. On the other hand, if this operator is relevant, then that means you would naturally flow to a different theory, which would have a smaller symmetry group, because you would have to have the symmetries preserved by this rank 4 operator. So in particular, that ends up being some kind of cubic symmetry group, which is a subgroup of O3. And so basically, that would say that this O3 model is like unstable to deformations to something called the cubic anisotropy CFT, which is close by. And so this was actually an interesting theoretical question for many years. Like, is the O3 model stable or not? And so the reason why it's an interesting question is because the dimension of this rank 4 operator is like very, very close to 3. And so people had done large n studies to like 5 loops. Like there's this crazy guy in Germany named Hagen Kleiner who wrote an entire 1,000-page book just about large n calculations of this theory. And every time you go to the next order, it would be above 3, be below 3. So this is one of these questions where like for some reason like nature was kind of like torturing us.
Is there any intuitive argument why it's because like 10 to minus 2 Kelvin, right?
I don't know. It's really a mystery to me. So people also use lattice to study this, but again, because the answer is so close to 3, it's like, lattice is not a completely rigorous method. I mean, you have to do extrapolations in volume, lattice size. Like I would say it was kind of unclear whether or not it was relevant or not.
About epsilon expansion.
Epsilon expansion is terrible. Epsilon expansion is kind of the worst of these things. Like usually large n is better. Epsilon expansion is usually worse. Epsilon expansion just kind of give you like a general idea. Okay, so the lattice from that paper suggested it might be 2.987, so maybe just barely relevant, but even a slight error would change this. So this is another example where we need high precision bootstrap studies. So we did that a couple years ago, and so we got an island here. This island was roughly the same size as the Monte Carlo estimate, so we didn't necessarily beat Monte Carlo in this case, but the advantage is that, first of all, our method is rigorous, and we were able to give a rigorous bound on the value of this rank 4 operator. So that's the plot that's shown on the right. So x is some linear combination of various scaling dimensions, delta s, delta phi, delta t. And the y-axis is the important guy, the scaling dimension of the rank 4. And so as you see, the scaling dimension of the rank 4 cannot possibly be irrelevant, because it's at most 2.9905. And so we basically rigorously proved that the O3 model is unstable. And so this implies that all Heisenberg magnets, which really exist in nature, that they are not described by the O3 Wilson-Fisher principle. Then instead they're described by this cubic anisotropy. And so,
Did you try to look for that CFT?
Okay, so it's a good question. So the next thing you could do is you could say like, okay, so why don't we study the cubic anisotropy fixed point? So first of all, one thing you could do is you could just do conformal perturbation theory, because this theory is clearly very close to the O3 Wilson-Fisher fixed point. And so I think people are working on that at the moment. This precise CFT data you need is a little bit tricky to extract. You have to look at other correlation functions than the ones we looked at.
But it means it's somewhere here.
Well,
there should be another.
Well, no, but this doesn't have O3 symmetry. The cubic anisotropy fixed point has a symmetry group, which is a subgroup.
Or it's like has discrete groups.
Yeah, it's a discrete group. That's the idea, because it's the symmetry is preserved by the rank 4 operator.
Okay, but why can't you do this?
You could do bootstrap with that symmetry group, and I think that's something people are working on. It's just a very big. It's a very big system, so it's hard to bootstrap. And also because it's so close to the O3 model, you would have to have really, really high precision to distinguish between them. But this is something people are indeed working on. And so this has experimental implications, because people study this theory and now they know that the critical theory is described by cubic anisotropy, not by O3.
But is it guaranteed that there is a CFT or can
The cubic anisotropy?
Right.
I don't think people doubt that theory exists. I mean, look, you never know a theory exists until you found it. But I don't know of any reason to think it doesn't exist. I mean, you could write down Lagrangian for it. It's just the O3 Lagrangian plus this rank 4 operator.
No, I mean, flows in the IR,
Yeah.
I'm saying, and gets strongly coupled there. So is it guaranteed that do we know that there is a gapless theory, or it's
Okay, you never know to the extent that like how do you know the O3 model existed? I mean, I would say you only really knew, because of the bootstrap and because of Monte Carlo, because of experiments, So it's like with any strongly coupled theory, you never know it exists until you have some strongly coupled method. So like, I agree that in principle, it could be that somehow it doesn't exist, but like, I don't know of any argument why it wouldn't exist. And considering how close it is to the O3 model, it seems reasonable it probably does. I mean, because you can certainly study a conformal perturbation theory. But I agree that like the ultimate proof would be to do bootstrap with this discrete symmetry and actually get an island for this theory. And then that would kind of
how conformal perturbation theory helps?
Well, I mean, conformal perturbation theory wouldn't prove that it exists. It would just allow you to estimate the data of that theory. Because that theory is very close to the O3 model, you do conformal perturbation theory starting from the O3 model using the data you computed from the numerical bootstrap, and then it gives you an estimate. Basically, it's an expansion in the difference between the two.
Do you find this in we find different fixed point when we do conformal
Yeah,
perturbation theory.
It means that I can do conformal perturbation theory and see the.
Sure, but I mean, but like that doesn't necessarily prove that it exists. I mean, conformal perturbation theory is always, you know, I mean, it's not a rigorous framework. I mean, you're doing an expansion in the difference of the scaling dimensions between the two operators, and so the difference is always fine.
But you mean there is some compensation between one loop and
Yes,
the
it's,
three level?
OPE coefficient is positive or negative.
I see. Okay.
Yeah.
So there is a fixed point.
Yeah.
If I not just like does one like analog of one loop
Yeah, it will be like
FPT then
0.01 delta t plus CTT
Yeah.
squared. But did you find the sign of this OPE coefficient? Is it positive or negative? I think you
The
don't.
OP coefficient which you need for conformal perturbation theory, as far as I know, has not been extracted, because for that you have to look at other correlation functions.
so you're saying it's not known what's the sign?
Yeah, that's
Yeah,
what
so,
I'm asking right now.
people have not done.
Because the flow.
Because
the way
if it's wrong sign, then you kind of know that there is no fixed point, right? So it is not identifiable by.
Well,
by
from the study we did, you could not extract the OP coefficient, which is needed to do conformal perturbation theory. So that's why, as far as I understand, it has not been done. But I also know that some people are working on it, not me. Okay. But it's an interesting question. Okay, so now we'll move on from these ON theories, which are the simplest theories, maybe a little dry for some people, and we can do a slightly more interesting theory, which is the critical Gross-Neveu-Yukawa model. So this now has fermions. So you have n Majorana fermions with an ON global symmetry, and it also has a certain scalar. It's a pseudoscalar called phi, which is an ON symbol. So those are the fields in the theory. You can write down some Lagrangian. It has a phi to the 4 term, and it has a Yukawa term coupling the scalar to the two fermions. And so just like in the Owen-Wilson-Fisher, this theory is strongly coupled in 3D, whereas it'd be like a free theory in 4D. So you could study it using the same, asymptotic perturbative expansions as in the Owen-Wilson-Fisher. You do large n, you do 4 minus epsilon, many loops. I think these methods work a little bit worse in this fermionic theory than they do in the critical Owen-Wilson-Fisher. So this is why there's kind of a stronger reason to want to use Bootstrap. Now you could also try to use lattice. The lattice is much, much harder though for this fermionic theory than it is for the Owen-Wilson-Fisher fixed point. So this is kind of like the first example of a theory which is clearly of experimental interest, where like methods prior to the Bootstrap aren't good enough. And so these lattice results exist, and I'll show you in the next plot, but you'll see they're very rare. In particular, it's hard for these lattice models to even distinguish between this critical Gross-Neveu-Yukawa model and some other closely related model. It's called the chiral icing model, which has a different symmetry group, but from the lattice perspective, it's hard to kind of tell the difference between the two. And so sometimes they don't even know which model they're studying. It's even confusing looking at the lattice papers. Okay, from the Bootstrap perspective, it's technically more complicated because you have to bootstrap correlation functions of spin half operators. And so this goes beyond what we discussed in these lectures. It's a slightly more advanced topic. But by now people have worked out all the technical ingredients you need to bootstrap spinning operators. And so the first study was done back in 2016 by these authors. And since then there's been various improvements. So let's go n by n, just as we did for the Owen-Wilson-Fisher. So when n equals 1, the n equals 1 Gross-Neveu-Yukawa model, this theory is particularly interesting because it was conjectured to have emergent minimal supersymmetry. So this would be kind of the first example of a supersymmetric theory you would actually find in nature. So if anyone ever says like, supersymmetry, who cares? It doesn't exist. You'd be like, no, it does exist. It's the Gross-Neveu-Yukawa model with one fermion.
Isn't the critical Ising? You could describe some critical systems.
Okay, maybe that. Okay, but that's like a little bit cheating because it's kind of like, well, it's because the theory could already completely solved.
It's not cheating, it's real world.
Sure. Okay. So I should say, other than the tricritical Ising model in 2D, this would be a theory in 2 + 1 dimensions where supersymmetry is not just something you kind of automatically solve for. This would be some strongly coupled, interesting phenomena. It'd be the first non-trivial supersymmetric theory that you could study in the real world. No, but I'm just saying it in the sense that it's completely solved. It's minimal. It's like you already know everything about it, mathematically. Like this Gross-Neveu-Yukawa model with one fermion, strongly coupled, you don't know that much about it, and so like if you found it with an experiment, you'd actually be learning new things.
Yeah, but this does not exist in the world. Well, by trivializing.
I think there are proposals of how to realize it. Anyways. So this theory, by definition of being a critical theory, it has one relevant parity even, what we call epsilon, and then large n studies suggest that it has 2 relevant parity odd operators, called sigma and sigma prime. And so this is believed, this was proposed in this paper by Fisher et al. To describe phase transitions of the boundary of phi + 1 topological superconductors. And so this is something people will be studying, hopefully in the near future, especially now that we have room temperature superconductors.
It's closed.
Sorry?
It's closed.
Closed? What's closed?
No, that it's not a superconductor.
Okay.
Yesterday there was a paper.
Okay, so I was joking. I was joking. Yeah. Now another curious fact about this is that actually no lattice results are available for this n=1 theory. So in this case, the bootstrap is the only game in town. So if we want to study this theory, which is experimental implications, it might have supersymmetry, we need bootstrap. And so here is a bootstrap study done by these authors just in this past year, and they get a precise island for this theory, analogous to what we found for Owen Wilson Fisher. So here you see the x-axis is the lowest parity odd operator, the y-axis is the second lowest parity odd operator, and they get a small island, not as small as the icing model, but pretty small. And then here on the y-axis, you compare the lowest parity even odd operator to the lowest parity even operator. And then this line here is what supersymmetry would predict. So if the theory had supersymmetry, you would expect these two scaling dimensions to be related by 1. And lo and behold, this island is consistent with supersymmetry. And so this island did not assume supersymmetry. This is something which kind of comes out from the bootstrap. So like you just assume that you're studying fermions, with like, I guess like a Z2 symmetry, and certain number of relevant operators. That gives you an island, and lo and behold, that island is consistent with supersymmetry. Now, the island is not small enough yet maybe to prove that it has supersymmetry, but I would say it's getting there. And so this would be very interesting, because this would be an example where you could prove the non-perturbative emergence of supersymmetry.
So what does this happen with that? There is a conjecture that there is
Yes, there's a conjecture there's emergent supersymmetry, and bootstrap results are finding an island which is consistent with that conjecture. But we could still make the island even smaller to really prove it. Okay. So another n which is interesting is n=8 gross novo Yukawa. So this has one relevant parity even by definition, one relevant parity odd. There's also supposed to be a fermion, which I just mentioned bigger than 2. This is physically interesting because it's supposed to describe phase transitions in graphene, and also time reversal symmetry breaking in D-wave superconductors, or so I'm told. So it's a physical interest. And in this case also, lattice results are only available for a different theory, which is the chiral icing model, which has a different symmetry. And so actually there's no lattice results available for this theory. So again, the bootstrap is the only game in town. And so also in this theory, islands were found by the same authors as in the previous slide, because they studied various values of n. And so here is a plot. So you see on the x-axis, there's a scaling dimension of this lowest fermion. The y-axis is the parity odd. This one is the parity even scalar versus the parity odd. And so this Monte Carlo isn't actually for this theory. And so that's why it shouldn't be surprising perhaps that the Monte Carlo is different from the island, because the Monte Carlo was for like a different but related theory. And in fact, if anything, you could say this plot proves that the lattice was not for this theory, because it's completely being excluded. This yellow is the epsilon expansion, which is like okay, but it's a non-rigorous approach. And it's reasonably close to the island, which I guess probably gives you more confidence that this bootstrap island really is the theory you care about. But I would just say that like this island is the best we know about this theory. Right? Okay, so hopefully I've convinced you that the bootstrap has been able to teach us stuff not just about the ON models, which are maybe classical models we already knew a little bit about before, but actually teach us about kind of interesting theories which are relevant to cutting-edge condensed matter systems, systems that people are studying today, like not back in the 60s. Okay, but now I'm going to talk about a future direction of a completely different class of theories. And so this is the family of theories called QCD theory. So this is quantum chromodynamics in 2+1 dimensions, with NF either scalars or fermions in the fundamental of the gauge group, which is UNC. So there's NC colors. And because we're in 3 dimensions, there could be a Chern-Simons-Level K, which is an integer. So first of all, this is not QCD in the real world, because that's in 4 dimensions. This is QCD in 2+1 dimensions, which will still have real world applications, but it's not related to the Oppenheimer rule. So this theory you can study perturbatively when any of these parameters, either the number of flavors, the number of colors, or the Chern-Simons coupling are large. And so there's been many perturbative studies of this theory in the past. But most physical applications are when these parameters are small. Now, it's believed to float a strongly coupled CFT for most of the values of flavor, color, and Chern-Simons coupling. But there's a lot of controversy, especially when these values are small, if it flows to CFT or not. So this is different from, say, the Owen Wilson Fisher or the Gross Novo Yukawa. In that case, I think most people are convinced that it's probably a CFT for every n. Well, of course, it's not proven, but I don't think there's too many doubts. But for this class of theories, there's a lot of doubts. And so another aspect of these theories is that they have an SUNF global symmetry when you rotate like the n flavors. When Chern-Simons level is 0, they preserve parity. But there's another flavor symmetry called U on T, where T is for topological. And this is special to the fact that we're talking about a 3D gauge theory. So whenever you have a 3D gauge theory, you can take your field strength F, you take the Hodge dual, and that basically defines a local current. And so that's why you have this unusual U1 symmetry. What's unusual about it is that none of the fields in the Lagrangian are charged under this global symmetry. So the only operators that are charged under it are things called monopole operators, which are basically defined to be charged under this U1 global symmetry. And so these monopole operators have also been studied in a large flavor expansion. Okay, so what is the motivation for studying QCD3, which is a whole family of theories? So it describes many different interesting condensed matter systems. In these condensed matter systems, both the gauge fields and the matter are emergent. So you shouldn't think of like these n fermions as actual electrons. You shouldn't think of like the colors as corresponding to like actual gauge bosons. Instead, they're things that kind of emerge. So in particular, QCD3 for various values of flavor, color, and Chern-Simons level describe phase transitions between fractional quantum Hall insulators at different filling fractions. So this was a result just from the last couple of years ago by Vishwanath, Yin-Chen He, various other condensed matter theorists. And so like basically the idea is that you have fractional quantum Hall effect, again, the different filling level, if you have transitions between those different filling levels, depending on like the specific fraction you have, this will end up determining the value of color, flavor, or Chern-Simons coupling in the CFT, which is supposed to describe the phase transition. And so, if one day condensed matter physicists are able to measure these phase transitions, we would then want predictions for them to see if we're actually finding these theories. This would also be interesting because this would just be a way of studying gauge theory in the lab in a much simpler context. You don't need like a particle accelerator to study gauge theory. You don't need nuclear bombs. You could study it, just using your tabletop condensed matter experimental apparatus. So another example of where this class of theories is of interest is QED. So when you have one color and 4 fermions, 0 Chern-Simons level. So in this case, this CFT describes not just a phase transition, but it's actually supposed to describe an entire state of matter. So this is very unusual. Like, usually you don't have a state of matter which is always conformal. Usually the CFT only describes the phase transition. But this is conjectured to be the exception. So this would be some kind of this is some bizarre quantity called an algebraic spin liquid. And like basically what the word means is that algebraic means that the critical exponents are algebraic, which is kind of the thing which is typical of a CFT as opposed to being exponentially small. And so there's conjecture that this theory describes the algebraic spin liquid, and there's even a specific material which is conjectured to be described by this system. So it's something called Herbert-Smithite, which you can look up and find a picture of it on Google. And there's a lot of controversy over whether or not it's described as algebraic spin liquid. And so I think to this day, it's still not settled. But this is a question people are actively working on. And so we need predictions for the critical exponents in this theory so as to measure it to experiments called this Herbert-Smithite.
So why there is no phase? Why it's not into phase transition? Why?
You're saying like, it's just a phase of matter which is conformal. I mean, it's something which could happen in principle. I mean, like the precise arguments of why this entire phase of matter is conformal, for that you'd have to look at the paper.
Doesn't mean that there is no relevant operators.
No, there's a relevant.
Then what does it mean?
No, that means that you then have to fine tune.
Yeah, but it sounds like you need to tune, right? There is
You need to tune.
They are definitely relevant operators. It's just an entire phase of matter which is believed to be conformal. So it's not describing
So it's not one point, just some.
Yeah, it's not one point. It's like some region.
But you still have to fine tune some.
You would probably still have to fine tune some parameters in Herbert-Smithite to get to that point, or to get to that region.
because if there is a relevant operator, you can turn it on with plus sign or minus sign, and I would say
Yeah.
this is
why I should.
this is a phase transition between these two phases.
Yes, that's what I'm.
Well, I mean, look, there are probably phase transitions between this conformal phase and a non-conformal phase. But I guess like the non-trivial statement is that there's an entire phase which is described by the CFT.
But what do you mean by that?
But this means like I can take like Z2 magnet and change pressure. And still describe as a same phase.
I think I don't know if it's precisely pressure, but I think that's basically what they're trying to say. Is that like there's some parameters you could vary such that it would just remain conformal.
Some parameters are coupled not to relevant operators, but to relevant operators as well.
Yeah, so I mean, I guess
So I wouldn't say something specific.
But if there is a neutral relevant operator, then
I mean, look, it's not like you're guaranteed to be in this phase no matter what you dial. I mean, otherwise we'd be seeing Herbert-Smithite all the time.
No, but I just don't understand what you mean by what is your distinction between calling it phase as opposed to like Ising model.
Okay. So I mean, perhaps the best way to say it is that I believe these people are claiming that as Fedor was saying, there are certain parameters which I guess coupled to irrelevant operators, such that you can even change them and it would just remain conformal. And I guess this is something which usually doesn't happen. Is that I guess usually the standard parameters you measure as an experimentalist, like say pressure or temperature or something like that, usually when you change them, there's only a specific value, which is the fixed point. Whereas here,
I mean, look, we already saw almost an example, I guess, of the superfluid helium phase transition, because there's kind of a whole line of your choice of parameters which all give you the CFT. And so I think the claim is that with this material, it's not only a line, it's like some kind of actual region.
So
How is it possible?
there's something that is coupled, say, to the temperature. It's this,
Well, if there is a relevant operator which is neutral under all symmetries, then it shouldn't be possible.
No, but it depends on what's coupling to the relevant operator. I mean, so like if you change external parameters which would affect that relevant operator, then I agree. But there could be external operators which do not affect that relevant operator.
You mean there are some marginal operator that?
No. I'm not saying it's conformal manifold. So like there's a question kind of, you have a given material, it's like how do you tune parameters such that you get to CFT? And so like in most materials, say like water vapor phase transition, you change the pressure and temperature, this is somehow related to the coefficients of relevant operators, and so you have to like tune it to get to the CFT. I think the claim about this weird algebraic spin liquid system is that some of the conventional parameters that you would tune as an experimentalist, I guess, do not affect the relevant operators.
Well, I understand some, but if there is no symmetry which protects relevant operator, then you need to tune some parameters.
yeah.
Well, okay, but I mean, it also depends on.
So
Look, okay, you have to. Okay,
so, all singlets are relevant.
No, there are relevant singles in this.
Then I can couple to them.
You could.
Yeah, but
I was never claiming that all couplings are relevant. I'm saying that there are different couplings, some relevant, some irrelevant. And I guess that is how this material is novel, relative to text model. Okay, I mean, you should read the original paper for this proposal. I don't know. I mean, I don't know if it's true or not. I'm just saying this is a proposal that this might be described by QED3. So another reason to be interested in this class of theories, beyond their possible experimental realization, is the fact that they are believed to have dualities. So as high energy theorists, we're used to duality. So like there's all kinds of superspectral theories that are dual. Zyberg duality between different 4D gauge theories. This is kind of the first way people first learned about confinement. But usually we thought that duality was something which kind of required supersymmetry, that it didn't actually apply to real world systems. And so what's interesting about this class of QCD3 theories is that for low values of color, flavor, and Chern-Simons level, they are conjectured to have dualities. And so, and not only are these interesting because they're not supersymmetric, but they're also interesting because you could see evidence for this experimentally. And some of these dualities would actually have experimental implications. And so, for instance, I think, like one of the original dualities, which was between, 3D QED3 with one flavor, this is supposed to describe like the transition between fractional quantum Hall insulators with filling level half. I think there's like some question in condensed matter literature of like whether or not like a certain, I guess, like effective action move written down describes this, whether or not like a certain, I think we call it particle hold, right? Z2 symmetry. And I think like if you have this duality, then it would, and if you don't have this duality, it wouldn't. And this would have some kind of experimental implication. And so it's a duality, which is interesting, I would say theoretically, and also has experimental implications. Now, one of these dualities was actually known for many years. So there's a duality called particle-vertex duality. That is a duality between the O2 Wilson-Fisher fixed point and scalar QED with one scalar. And that's been proposed since the 70s. So the novelty of these dualities, though, is that these were dualities between some theories which had fermions and some theories which had bosons. So that's why you could say it's an example of what people call 3D bosonization. And so these dualities were proposed by Witten, Wang, Stenzel, and Zyberg back in 2016, also by Karch and Tong the same year. But they're strongly coupled dualities. And so there's no real evidence for it.
So these are dualities in the sense that you start from different theories and they flow to the same IR theory.
So they are IR dualities.
It's IR duality, not along the flow, right?
Yeah, no, not along the flow. So that's why it's in some sense more interesting than maybe trivial dualities in 2D. Okay, so there's a lot of interest in these theories. They're also very hard to bootstrap though, because when you're bootstrapping a gauge theory, the only input to the bootstrap usually is the flavor symmetry, not the gauge symmetry. So how do you distinguish between different theories to the same flavor symmetry, different gauge theory? So the first study on this was done by me and Sylvia back in 2016. So here's a plot. We were focusing on 4 fermions, QED3, Chern-Simons level 0. The x-axis is the lowest charge monopole, the y-axis is the second lowest charge monopole. We're doing the scaling dimensions. And so this first result is that we got various upper bounds which would change depending on some assumption we made in the spectrum. So like we would assume that a certain non-monopole operator would have a certain scaling dimension of at least a certain value. And this was just something we had to put in to get interesting results. And so the claim is that there was a certain value of this gap, 3, such that we got a kink which matched the large flavor estimates for both multiple operators. So the non-trivial thing is that we put in one number and we got out predictions for 2 numbers, both of which matched largely. And so this was kind of like a first baby step towards, maybe finding this theory and solving it using the bootstrap. Of course, this is just a kink, and also we had to kind of put in this unjustified assumption of the gap of one of these non-multiple operators. But since then, our study was improved. So in this past year in 2022, there's a nice paper by David Poland et al., where using many, many other assumptions and a bigger system of correlators, they managed to get an island for the first time, which matches exactly the kink we had predicted back in our 2016 paper. And in particular, it also matches the large N prediction. And so it seems like we're getting closer and closer to actually non-perturbatively numerically solving at least one example of QCD3, which is QED3 with 4 for. Now, of course, there were still a lot of assumptions that went into this paper, and so it's still not like ideal. It's not as justified an island as, say, like the icing model island, but it's also a much harder system. And so it's expected that it will require more work. So this is just to give kind of like a taste for QCD3. And so there's many more things to do for QCD3. So first of all, we want to get a better island, even for QED3 with turn summons level 0. There's also a question of like, for what value of flavors is QED3 even a CFT? Because many people believe that when the flavors are very small, there just isn't a CFT. So that's something we would like to prove. So like, is the critical value 2, for instance? And so in particular, there's some claims that there might be a merger annihilation scenarios. It might be 2 different theories, both which have the same global symmetries, but they differ by the number of relevant operators. And it might be that as NF becomes smaller and smaller, they eventually merge and go off into the complex one. That's one thing which could be happening. And so the hope is that we can do precise bootstrap studies for this entire family of theories, get precise critical exponents, both to guide future experiments, as well as to prove dualities. Because the way you would prove a duality is you would put in the symmetry that's supposed to hold on both sides of the duality, and you put in assumptions about the number of relevant operators that's supposed to hold on both sides. And then if you can prove that the lab region is just a tiny island, that would basically be proving the duality. Because you'd be proving there's just one CFT consistent with these general assumptions. This is related to the fact that duality is basically the same thing as universality. And so I should actually say there's been some intriguing evidence, paper of mine with these condensed matter colleagues just in the last few months, showing how you can use the large flavor expansion to kind of analytically compute the scaling dimensions of multiple operators, and that seems to be consistent with these dualities. So we already have some kind of intriguing evidence from the large flavor expansion for these dualities. It would be nice to put that on a rigorous footing by actually doing numerical proofs. Okay, so this finishes the condensed matter part of this review and future direction. So before we move on to the quantum gravity part, any questions about the condensed matter part? Okay, good. So I will move on to the quantum gravity. So the basis of why conformal bootstrap is relevant to quantum gravity is that the way we define quantum gravity is using ADS-CFT. So you take quantum gravity in anti-de Sitter space with negative spacetime curvature and d+1 dimensions, and this is supposed to be dual to CFT in one less dimension. And so when the CFT has many degrees of freedom, i.e. when the number of colors is large, then the quantum gravity is supposed to be described by Einstein gravity, where the idea is the 1/n expansion gives you the expansion where the coupling in gravity is small. So another aspect of this dictionary is that the correlators of the stress tensor operator in the CFT are dual to graviton scattering in ADS. So if you can bootstrap correlation functions of stress tensors, that means you can study graviton scattering in ADS and quantum gravity. And in particular, you can study this graviton scattering not just in ADS, but there's a precise way of taking the flat space limit of ADS. So if you first study graviton scattering in ADS, you can then take the flat space limit and then learn about graviton scattering in flat space, which is the S matrix. So this kind of resolves like an objection people sometimes have, which is that, oh, ADS-CFT teaches you about anti-de Sitter space, but we don't live in anti-de Sitter space, who cares? And so that's actually not true, because ADS-CFT teaches us about flat space as well. There's a known way of taking the flat space limit. Now, it doesn't teach us about de Sitter space. So if you hear about de Sitter space, then you're out of line. At least for flat space, you can learn about it from ADS-CFT. So we're going to focus on the simplest examples of ADS-CFT, which is where the CFT has maximal supersymmetry, which is also the original case where a log theory was first proposed. So this limits us to CFTs in dimensions 3, 4, and 6. But the question about these holographic theories is that they're all very strongly coupled, just like the condensed matter systems we were talking about. And so this is why ADS-CFT was kind of only half of a solution. Sometimes you'll hear kind of like popular articles which say like, oh, the problem with quantum gravity was solved in ADS space. Now, of course, there's many reasons why that's not true. But one reason that it's not true is that we just shifted the problem from studying quantum gravity, which is super, super hard, to studying holographic CFTs, which is still super hard because they're strongly coupled. We don't know anything about strongly coupled CFTs without strongly coupled methods. So to make the dream of ADS CFT true and to really say we have solved quantum gravity in ADS, you have to solve the CFTs that are dual to quantum gravity. And I will try to convince you that the way to do that is using Bootstrap.
That's just the first step.
That's the first step. Yeah, so this is the first step towards solving quantum gravity in ADS.
Well, the numerical forecast and the BGMs for sure. So they're,
No, but those are also strongly coupled.
well, but they're integrable, right? So
No, but they're integral only to leading order at large n.
no, I think not.
No, what do you mean? I know of no results beyond leading order at large n for integrability.
Well, I think that at least that's my understanding of what Pedro would say, that you can just calculate one. Well, the integrability also governs one of an expansion, right?
I mean, he might say that, but he has never computed anything beyond leading order at large n.
well, they're trying to, but
We also need non-perturbative effects.
Yeah. I mean, from my understanding of talking to Pedro is that he hopes that you will one day be able to do integrability beyond leading order at large n, but there are 0 results so far. So like the only thing they have is if you take a limit where n is large and the rank of operators is large, in the simultaneous limit, you can go beyond leading order at large n, and even in that limit, you can only compute things approximately. But like you can't compute, for instance, like the scaling dimension of the Konishi operator beyond leading order at large. So another way of saying this is that what is integrable is the classical string theory, because that's leading order at large n. There are no integrability results that are known of, to my understanding, about quantum string.
but from string theory perspective, basically the statement is bullshit theory is integrable. And
Classically.
no, bullshit, full bullshit. In all orders to alpha prime, it's integrable.
Sure.
So bullshit is
but only
integrable.
leading order in G string.
Yeah, but G-string expansions, that's just calculated on different topologies. It doesn't change the fact that bullshit theory is integrable.
Yeah.
So I think.
I don't know if this is so obvious though. I mean, like I know of many examples where you have enhanced symmetries in leading order and large n and not beyond.
I
I
think
can give
it's
you
not.
that.
It's not the claim that
Yeah.
like at finite n one would be able to solve it exactly. But I think integrability would allow. I think that's the claim.
Look,
It would allow to calculate one-way corrections
I
exactly.
certainly hope you're right,
Right.
but no one has been able to show this so far. And so if somebody shows it, that would be an incredible, profound result. But until we've shown that, I think, and also so certainly a finite n, I don't think you would expect to choose it.
Yeah. Right. Yeah.
Okay. Anyway, look, I'm not anti-integrability. I think it's an amazing method and it's complementary to what we do. Okay, so let's start with n equals 4 super mills. So a brief review of this theory. So all maximally supersymmetric n equals 4 CFTs have SU4 global symmetry and a one complex dimensional conformal map. This is without even assuming n equals 1. It's just based on symmetry. Now, the only known theories with maximal supersymmetry are supermills with a compact gauge group, say for instance SUN, and a complexified coupling, which is related to the gauge coupling as shown. So we care about this theory for many reasons, partially because it's dual to type 2B string theory in ADS5 process 5, where the string length is related to n as shown, and this complexified string coupling is just the same thing as the complexified gauge coupling. So in other words, we say that we have Einstein gravity at large n, because when n is large, G Newton is small. So there is a regime where you can compute this thing, which is when it's weakly coupled. And then you can use Feynman diagrams to compute as many orders as you want for any value of n. But of course, that's not the regime we care about, because that's the opposite regime of the regime where you have an Einstein gravity description. So you'd be describing like super, stringy theory. Now, another regime, which Sergey just brought up, is a leading order at large n, but for finite Tufts coupling, you can use integrability to solve the theory, compute the entire spectrum. And this another way of saying is that the classical string world shape is integrable. But as we just discussed, we have not been able to do anything about this beyond leading order at large. And it seems extremely hard. And so the two questions are, first of all, how do we study large n to subleading order, to study the quantum string? And the second question is, even more boldly, how do we study finite n? And so if you wanted to eventually learn about things like black holes, you would almost certainly have to do finite n. So I don't think you would ever learn about black holes and integrability, even if you did integrability to a billion orders. There's even a paper by Witten, I think, about that. Okay. So what is the bootstrap approach to studying n equals 4? So let's study the stress tensor correlator, because that's what's dual to graviton scattering. And let's just assume superconformal symmetry, and we can input the value of n because it's proportional to c, which is the coefficient of the stress tensor 2. So this was originally done by Leonardo back in 2013 with collaborators. And so what's the data which shows up in this 4-point function? So basically everything is fixed to be trivial except for one class of operators, which are long multiplets with even spin and scaling dimension bigger or equal to spin plus 2. So this is the thing we're trying to compute, these long multiplets. Now, in the original study, though, they didn't know how to input the value of tau. And so that's why the bounds they got were kind of, in principle, on the entire conformal map. The reason it was hard to put in the value of tau is because there was no quantity which was known as an exact function of tau. And so the novelty in this paper I had this past year with these collaborators is that we figured, or that's actually from a couple years ago, so we figured out how to compute a quantity as an exact function of tau, which can be related to the 4-point function. And so the way you do that is you take the mass to form free energy, which is what this F is, and you take 4 derivatives in either the mass or tau itself. And then you set mass equal to 0. And because mass and tau are coupling to the stress tensor, this just gives you integrated correlators of the stress tensor. So as many derivatives as you take, it's an endpoint correlator of the stress tensor with an integral. So this was kind of the first step. And so the reason why we care about this mass form free energy is that localization can be used to compute it, as shown by Pestum back in 2007, in terms of an n-1 dimensional integral. And it's a non-trivial function of tau. You can do this for any value of n. Although, of course, it's an n-1 dimensional integral, so as n gets bigger, it gets harder and harder. And so the second ingredient we used is that it was shown back in 2017 by these authors how to impose integrated constraints on the numerical bootstrap. So they did that in 2 dimensions, but then we generalized this to 4 dimensions. And so this is something which was not covered in the class. It's a bit more advanced, and it's a method just developed in the last couple of years. And so let's first start with the results about bounds on n equals 4 with no localization inputs. So these bounds are supposed to apply to any n equals 4 theory, not even necessarily superangles, just any theory with n equals 4 supersymmetry. So on the x-axis, you have 1 over c, where c is basically n squared. And so that means this is basically n goes to infinity. On the y-axis, we have a simple scaling dimension. So the scaling dimension of the lowest dimension spin 2 operator. And so the bootstrap bound is this black line. And so this is just an improvement of bounds from Rastelli's original paper. We just went to much higher bootstrap precision. So the black line is the bootstrap bound. And so these various colored lines, these are predictions for specific theories. So you can study n equals 4 superangles and a large n expansion using Witten diagrams. So the leading large n, or large C, is what you would get just from tree-level supergravity. And that is actually universal to any theory with an ADS5 factor. So it doesn't care about the compact space-time factor. And so that's what this gray line is. So it's a line because it's just linear. And so what's nice is that at very large n, you see that this gray line is right on the boundary of the bootstrap bound, which is something which didn't have to happen. So this kind of shows that this bootstrap bound, at least at very large n, seems to be kind of the best possible bound, and that it really is saturating this ADS5 supergravity. But so say we want to distinguish between different theories. So we want to be sensitive to the compact spacetime factor. So for instance, you could have n equals 4 superangles with SUN gauge group. That's ADS5 process 5. You could have SON gauge group. That's ADS5 process 5 mod Z2. Or you could have some exotic theory with no compact spacetime. So this would be an example of scale separation of the most extreme variety, where you just don't have a compact spacetime factor. And so this theory, there's no known CFT dual, but you could just define it from the bulk as just a theory which doesn't have any light single trace operators other than the gravity. So there's no KK modes because there's no spacetime factor. And so you can then compute this CFT data at one loop, so 1 over c squared. And so this is a correction to the gray line, and we get different corrections for each of these different theories. And so what's very interesting is that it turns out that the theory that continues to saturate the bootstrap bound at largish n is the pure ADS5 theory, not ADS5 process 5 or ADS5 process 5 mod Z2. So this is very surprising, because this bound is a totally general bound. We didn't put in the value of tau. Nonetheless, you would have thought, but this one loop correction doesn't depend on tau. And so that's why this is a good thing to compare. And you would have thought that okay, maybe n equals 4 superangles for a specific value of tau is saturating this most general bound. Turns out no. And instead, the theory which is saturating is this pure supergravity theory of ADS1. So now you can do something more. So instead of just doing a general bootstrap with no localization constraints, you can now input localization constraints. So now you've specified the n equals 4 superangles because you're doing inputs which are specific to that theory. And so let's focus on the SU2 theory, because that's like the simplest one, lowest value of n. And so we put in these localization inputs. Now we can compute bounds as a function of tau. I actually have a talk about this exactly here a couple of years ago, for those who were there. And so here are these bounds you get with this new orange light region. The gray dotted line was the old bounds, which we didn't put in localization. And the non-trivial thing is that we find in the weak coupling regime that CFT data matches these bounds. And so we can only compare it to weak coupling for smallest G mills, but the fact that it matches with such a huge regime gives us confidence that probably even for strong coupling, our bounds are still corresponding to the physical data. And so this is a result which I'm very proud of, because I think this is basically the first step to non-perturbatively solving n equals 4 superangles. Because if you believe that this bound really is corresponding to n equals 4 superangles, which I think we have good evidence for from weak coupling, then we just have the solution, for every value of coupling. And the right-hand plot also shows, very large values of coupling, in particular, where you go from a special value of tau, which has Z2 enhanced symmetry, to a special value which has Z3 enhanced symmetry. These are very special points on the conformal map. So another thing you learn from this plot, though, is that you see that this gray dotted line is excluded for all values of G angos. And so this is further evidence that the most general bound, which applies to any n=4 theory, just never corresponds to n=4 super angos. So at large n, we already knew that, because at large n, this plot showed that the n=4 super mills, which was blue or purple, was not saturating the most general bound. But maybe it would have said like, okay, fine, maybe at large n it doesn't saturate, but maybe at really small n it does. This plot proves also at the smallest value of n, the most general bound is completely unrelated to n=4 super angos. So then you could ask, okay, but what theory is saturating this most general bound? And so a conjecture is, at large n, we saw that pure 8-5 supergravity is saturating the bound. And so perhaps also at small n, pure supergravity is saturating the bound. This is a very bold conjecture, because pure 8-5 supergravity, at large n, you could always describe it as some effective theory, fine. But most string theorists would claim that it's not well-defined, non-perturbative, so that it doesn't mean anything in finite n. They would say that because we don't know of any string completion. This is just pure 8-5 supergravity. It only exists in 5 dimensions. But these bounds are kind of suggestive that perhaps there is such a theory which can be defined, for every value of n, which I think would be very interesting. This would be like an extreme example of scale subdivision. Okay, so moving on from 4D CFT duals, so now we have a quantum gravity with the 3D dual, and this is ABGM theory. So in this case, the global symmetry is SO8. All the known theories are these gauge groups with 2 gauge groups and a Chern-Simons level. And in particular, when the Chern-Simons level is 1 or 2, you have maximal supersymmetry. In this case, the theory can be dual to either M theory, when Chern-Simons level is finite, or string theory, when Chern-Simons level is large. But maximal supersymmetry is when Chern-Simons level is 1 or 2. So that's what we'll focus on the most. This theory is also strongly coupled. And so again, we would like to be able to study it using conformal bootstrap. And what's interesting about this theory, supposed to n=4, is that this is our only way of studying M theory. And so if you want to study M theory, you better study ABGM, because I just don't know of any other way to study. Okay, so we're going to bootstrap the stress tensor because that's dual to graviton scattering. Now there's many non-trivial multiplets that appear. You have long multiplets, you have various short multiplets. And the localization input now is that we can compute the OP coefficient of certain short multiplets. Analogous to how we compute the integrated constraints in n=4. So here are some bounds. So these bounds, first, are without localization. So these are just general bounds which should apply to any maximally supersymmetric theory in 3D. And you see a very similar story as what we saw in 4D. So you see that at very large n, the supergravity approximation, which is the gray dotted line, you have to look at very, very large n, but at very large n, it's saturating the bound. This is for a scaling dimension, this is for some non-trivial OP coefficient. But then you see as you go to slightly smaller n, you can take into account the one loop correction for either pure 8-4 supergravity or 8-4 crosses 7, which is supposed to be dual to M theory. And then you find that in the largest n region, the thing which is saturating the bound now seems to be the pure theory and not the theories that are dual to M theory. So with this plot, it's a little bit hard to see because you have to look at very large n. With this plot, things are a bit better converged. And there you can very clearly see that this orange line lies right along the black bootstrap line, as opposed to blue and purple, which kind of go all the way up. So this is just showing that what we saw in the 4D case, it's not just some fluke. It seems to happen also in 3D. So this seems to be a general phenomenon. That pure supergravity seems to always be the guy that saturates the most general bounds. Okay, so now here is a bound which focuses on the OP coefficient, which should be computed from localization. So in this bound, the black lines are bootstrap bounds, upper and lower bounds, and the colored lines are the exact values from localization. And so this just shows that the localization values are not saturating this bound. I mean, they're close, but not quite. And so this was done for every value of n. So this shows you even at small n, the most general bound is not corresponding to the M theory. Kind of analogous to what we saw for n=4, how we focused on n=2, and we saw that the most general bound was not being saturated by n=4 supergravity. Okay, so here's a mixed correlator bound, which kind of has similar content. Here's a bound where we focus on large n, and it's a little bit hard to read this plot, but I'll try to walk you through it. So the gray lines upper and lower is the most general bootstrap bound. And then the black lines upper and lower is after we put in localization. So that's after we've specified to a specific theory as given by localization. And it's a little bit hard to see, but if you look carefully, you can see that that this gray line moves slightly up to the black line after you put in localization, and that slight improvement is in the right direction, because after that slight improvement, now the one loop correction for ADS4 across the 7, which is what this red dotted line is now closer to saturating bound. Although I'm not going to say this is like a slam dunk result. I mean, like, clearly you need very high precision to see these small differences. This is still kind of a work in progress. Okay, so here I've discussed that both for 3D and 4D holographic duals, there seems to be a similar story, which is that the most general bounds correspond to pure supergravity, whereas if you want to find the theory that's actually dual to string theory M theory, you have to put in localization. But after putting in localization, we found evidence in both cases that you really do find the theory that is dual to quantum gravity. And so there's some hope of actually numerically solving, at least low-lying data to some approximation using Bootstrap. So there's many future directions though. I mean, this is an emerging field. It's only from basically the last year or two that we have all these results. So first of all, we would want to compute our localization inputs for every value of n and tau. Because right now we just have them as n-dimensional integrals, so it's very hard to do that at large n. So for n equals 4, one of these inputs has already been computed at finite n in a very interesting paper by Michael Green. But we'd like to do it for the other quantities, basically this 4 derivatives of mass. So this is actually something I'm working on right now. We're actually very close to having some results. So that should be out soon. And so, I mean, one of the motivations of doing that is that we could then try to solve n equals 4 square mills for every value of n, not just for small values of n. Another thing we would want to do is not just get an upper bound, but get an island. So the idea that would be that for every value of tau, you should get both an upper and lower bound, which are very close to each other, and that would really be rigorously solving n equals 4. Because then you wouldn't have to assume that the theory saturates bound, you would just have an island. And like the way we would try to do that is kind of analogous to what was on an IC model, basically by imposing that a certain number of operators are singlets. So like from weak coupling in large n, the intuition is that n equals 4 has 2 relevant singlets. One of them is the Konishi, and the other one is basically the lowest dimension double trace operator. And so we suspect those are probably the only relevant singlets in general, so maybe we can impose that and thereby get it. If we could get such an island, or even from the existing results, if you assume the theory saturates the bound, you could read off the spectrum, and then you could see all the operators that appear in this 4-point function. And then you could understand all kinds of interesting things about how the gravity emerges as you dial n and gravity, Ln and the coupling, to be large. So one thing you could do is that at leading order at large n, you could compare to integrability, where you already have results for every value of the coupling, but you could go beyond integrability by looking not just at leading order at large n, but really any value of n. And so this could even give a prediction for integrability. So say one day integrability manages to go beyond leading order at large n, then they would have some predictions from numerical bootstrap to compare it to. Now, being very ambitious, if we could, if we end up getting an island for n equals 4, for every value of n in coupling, and if we can read off the spectrum, not just of the lowest operators, but say the lowest 10 operators, which hopefully should be possible in the future, then we could try to understand things about black holes. Because there's an intuition that black hole states should correspond basically to unprotected states whose twist is big. And so in particular, if the twist is roughly scaling like c, that's like roughly what a black hole state should be. And so this means you have to look at high dimension operators, so that's a little bit difficult from the current bootstrap, but this is something we'd hope to do in the future. And say you could read off the spectrum really precisely for all operators of dimension 20 or lower, and then you could just kind of see as you vary n in the coupling, say the density of operators between 10 and 20. And presumably there'd be some prediction that once you're in the gravity regime, there'd be a certain expectation of how many such operators you should have. Presumably that exists. And whereas if you're in the non-gravity regime, you would just have some generic spectrum, such that you would have, for instance, for some weakly coupled gauge state. And so it'd be very interesting to see if you could actually see the spectrum emerge.
Maybe see whether you have random statistics.
Yeah, or random statistics. So you'd have to define randomness in some precise way, and then just see if you have these random statistics from the spectrum. So this is an example of something we would like to learn from Bootstrap in the future, and something you would need Bootstrap for. So you could ask kind of the analogous question in the IC model. It's why in the IC model do you need these super precise numerics? Why do you want to read off the lowest 20 operators? In the IC model, maybe you don't care so much. But if you could do the exact same thing in the IC model now for n equals 4, then you'd be able to learn about black holes, which I think is pretty cool. And so that's why I think that while the Bootstrap is interesting for condensed matter, I think it's super interesting for quantum gravity. That's where I think kind of the biggest questions lie. Okay, so a future direction in the context of ABGM theory, so analogous to n equals 4, we'd like to understand these integrated constraints better, compute them for all values of n in coupling. We haven't even imposed integrated constraints in ABGM yet, so that's something which should be done in the future. And just like in n equals 4, ideally we'd be able to isolate the theory, read off the spectrum, and also see the emergence of gravity as we make n become bigger. This would be in the context of M theory. Another interesting thing you could do though with ABJM is that there's kind of more parameters you can vary. So we have N and coupling, and there's also 2 gauge groups. And so there's 3 parameters, the 2 gauge group colors and the Chern sinusoid. And as you vary these 3 parameters, you can go from M theory to string theory to higher spin gravity, which are kind of like the 3 families of theories of gravity which we believe exist, at least above 2 dimensions. And so that means in principle, if you get islands for all 3, then you'd be like solving all of quantum gravity, from one holographic dual. And you'd be able to kind of see how they interpolate between each other. You could see like how higher spin gravity emerges from string theory, all kinds of interesting questions of that type. So another practical thing which might be a little bit easier, would just be to read off one of rank corrections from the numerics for the stress tensor correlator in ABJM. Because if you could read off these corrections, this is dual in gravity to higher derivative corrections to M theory. And in some sense, this is the definition of M theory. So M theory we know much less than string theory, because in string theory we have the world sheet, which in principle allows us to compute things to any order, even if it's very challenging. But for M theory, we don't have a world sheet. So with M theory, we don't even have an in principle method to define it beyond the lowest couple orders where you can use dualities to relate it to string. So that's why M theory is very mysterious. And so it might be that the only way to even define M theory is using Bootstrap, i.e. solve ABJM at large N numerically, read off these corrections by doing curve fitting to the Bootstrap bounds, and then give predictions. So the first question would be, there's a lot of conjectures in literature that the first unprotected high derivative correction of M theory, which is the D to the 8 R to the 4 correction, some people claim that's 0. And so this is a very clear signature. So we should be able to see with Bootstrap, is it 0 or not? And so we would just have to get sufficiently precise numerics such that first of all, we can match all the previous corrections to make sure that we're looking at the right thing, and then give a prediction for this correction and see if it's 0. And there's even bolder corrections even claiming that a whole infinite family of high derivative corrections are 0. So these are all things we would hope to check using Bootstrap in the future. Okay, another future direction is the 62, 0 theory. And so this is kind of the most mysterious CFT. Some people claim it's the mother of all quantum field theories, because by doing dimensional reduction, starting from 62, 0 theory, you can get n equals 4, and then from n equals 4, you can get various n equals 2 theories, et cetera, et cetera. So there's a wealth of work which has been done starting from this theory. It's also the highest dimension which we believe is interacting CFTs. But this theory is very mysterious. We don't have a Lagrangian because it's in 6D, and so the only way we know to construct these theories is from string theory. And so they're classified basically by Lie algebra, although they're not gauge theories. It's just a classification. So you can have either SUN, SON, or these exceptional groups. And so when it's SUN, it's supposed to be dual to 87 cross 4, and it's supposed to SON, it's supposed to be dual to M theory and 87 cross 4 mod Z2. So you have an ABCFT dictionary analogous to ABJM. And this theory is always strongly coupled. And so this is kind of a natural theory to study with the Bootstrap. And so this Bootstrap was initiated by Leonardo et al. Back in 2015. So again, they studied the stress tensor correlator.
What is the argument? Why it's highest dimension?
Well, you don't have a superconformal algebra in dimensions above 6.
It could be supersymmetry.
Without supersymmetry, in principle, they'd be interacting CFTs, and that's an interesting question. No one has found. Okay, so I'm just saying that this is the highest dimension in which we know of an interacting CFT. There could be non-supersymmetry. I mean, that's one of the big outstanding questions in CFT. Okay, so when you study the stress tensor correlator, so what appears in the 4-point functions, you have long multiplets, then you have various non-trivial short multiplets. And so as usual, we compute things as a function of n. But before we show those bounds, we can also bound C itself, or we can bound n itself. So we could basically say, from a general perspective, what is the lowest possible value of C, which is supposed to be related to n? So this is something Leonardo did in their paper back in 2015. So this is a plot from his paper. So the x-axis is the Bootstrap precision. The y-axis is this bound on C. And if you interpolate their precision to infinity, like this, it seems like the bound is converging to 25, which is indeed the smallest value of C, which is known, because the lowest 62, 0 theory has C equals 25. And so this is kind of interesting because this suggests that this general Bootstrap, might be used to study the this non-trivial theory. Although this requires a certain extrapolation. And, you always have to be careful about extrapolations when you do numerics. So more recently, we studied CFT data. Just as we did in 4D and 3D, this is the most general bound, so not assuming anything about the theory. And we found a very similar pattern as what we saw in 3D and 4D. So just like in 3D and 4D, we saw that at very large n, tree-level supergravity saturated bound. But once you went to slightly smaller n, it seems that the pure theory was saturating the bound, and not the one which was dual to string theory M theory. It's the same story in 6D. It's just a little bit harder to see in 6D because convergence is much worse in 6D than in lower dimensions. But if you look closely, you can see in these plots that at very large n, the gray line is saturating the bound, And then as you go to smaller n, the orange line is the one that's closest to saturating the bound relative to these other colors. Although you kind of have to squint here relative to the lower dimensions. And so this also suggests that you would need some extra input such as localization if you wanted to study the theory dual to M theory using Bootstrap. So the future directions for 6D is, it's much harder to study than lower dimensions because it's a non-Lagrangian theory, so you don't have localization. So it's kind of like, what else can you put in? Now you could try to kill the pure ADS7 theory by looking at some mixed correlators of light single trace operators that just by definition don't appear in pure ADS7. So you could look at a 4-point function of half APS operators at rank P where P is bigger than 2. Because this would basically correspond to KK modes, and so you'd be putting in by assumption the fact that there are KK modes. So that'd be one way of killing the pure ADS theory. Another thing is that even though you don't have localization, you do have something else which is kind of similar to localization, which is the 2D chiral algebra. So Leonardo et al. Showed back in 2014 that there's a subset of protected operators in 6D which are described by a 2D chiral algebra, and you can use it to compute everything about them. Particularly, you can compute their OP coefficients, which are non-trivial. Now, specifically for the stress tensor 4-point, this wasn't useful because the 2D chiral algebra in this 4-point is trivial. So you have to look at another 4-point function, such as the next, the 4-point function of 3333, so rank 3 half APS operators. In that case, the 2D chiral algebra is non-trivial, and you can use it, as I showed in this paper with Eric Perlmutter from 2018, to compute a certain OP coefficient, which takes this very non-trivial answer. So you see it's some ratio of n and c. And so in principle, if you were to bootstrap this 3333 correlation function, you could put in this value, and then hopefully that would allow you to actually study this actual theory dual to M, kind of analogous to what we did in 3D and 4D. So this concludes our discussion of quantum gravity future directions. Now, so any questions before we move on, I guess, to kind of more general future directions?
Yeah, it was, can you go back to your slide on the ABJM and showing pure ADS4? Was that ruled out? I was kind of confused with that.
Okay, so
because in the other plots it hugged the bootstrap bound.
Okay, so the thing is that we're comparing large n approximations to what's in principle finite. And so the large n approximation is an asymptotic expansion. It's only supposed to work for sufficiently large. It's always an art comparing, an asymptotic expansion to a finite thing. And so you just have to look at sufficiently large n such that you think your asymptotic expansion is a good expansion. And so, like, when you see this orange line being in this disallowed region, this probably just means that the asymptotic expansion is not so good in that region. I wouldn't say, like, it doesn't prove that it's like ruled out. It's just like, you would have to probably compute this 1/n expansion to higher order. Even if you did compute it to higher order because it's asymptotic, it might be that it stops converging. So I would say, like, the reason to believe that it's good in any regime is because for sufficiently large n, it does saturate. And that's what gives me confidence that this is a useful metric at all. And then I only trust it, in the regime where it's not becoming totally crazy.
But this is still much worse than, I guess, for ADS5. It looked like it was.
Yeah. So, it's worse. First of all, because it depends kind of like what regime of large n you're looking at. So it's like the x-axis, I'm showing you a certain slice of large n. And so, like, it's kind of like, which slice did I show you?
Right.
So I think in the 4D case, I was showing you much bigger.
Okay.
So you can always kind of cheat. It's like this is why whenever you hear talk about numerics, you always have to be very careful. There's all kinds of ways of cheating with numerics. I mean, you can show, like, which range the x-axis, like, even politicians cheat with these kinds of things. So yeah, people do all kinds of extrapolations. You have to be careful. Okay, so what are some general future directions? So first of all, most of the results without supersymmetry were in 3D that we discussed. But what about 4D? In fact, most CFTs in 4D are gauge theories, which is why they're so hard to study. Because the bootstrap only puts in the global symmetry, it doesn't put in the gauge theory. And that's why there's been so few results for gauge theories if you don't have supersymmetry. And so a classic result we'd like to understand, which is related to confinement, is the conformal window of QCD with n colors and nf labels. So this is a classic question which existed for many decades. We know the upper value of this window. So when nf over nc is 10 nc over 2, then beyond that, you don't have a conformal theory. The reason why you can prove that is because in that regime, the theory is actually weakly coupled. And so you can this just comes from like Feynman diagrams. But the lower value of this window is where the theory is strongly coupled, so you can't use Feynman diagrams. And so the way people have studied this was using lattice QCD, but it's a very hard thing to do using lattice QCD because you're kind of trying to find where something is conformal, and that's kind of like the hardest point to find with the lattice study. And so there's various estimates. So for instance, when you have 3 colors, as reviewed in 2016, people estimated the number of flavors should be around 12. But my understanding, talking to lattice QCD people, is that this is not a completely agreed upon calculation. So there's been many different estimates. And so this would be a very good thing for Bootstrap to study. But it's hard. So one possible approach is that if you did a bootstrap study of currents, then there's a certain anomaly which would appear in that 4-point function, one of the OP coefficients, and that anomaly is fixed in terms of the number of colors exactly. And this would be a way of inputting the number of colors into the bootstrap. And so this might be a way of going forward. Another approach is to maybe continue studying theories with supersymmetry, but reducing the amount of supersymmetry. So far we've had some nice results for n equals 4. What if we could also study SQCD in the conformal case with n equals 2? So I actually had a paper on that last year, where it seems like localization plus bootstrap also solves the theory, and that's kind of a step in the right direction. Because it went from n equals 4 to n equals 2, maybe we'll eventually get to n equals 0. But this is certainly an outstanding problem which we'd like to solve in the future.
That localization will be gone.
Yeah. I'm just saying, we could maybe learn some general principles, like what does a distribution of operators look like? Because maybe something like that wouldn't matter so much about source. Yeah, of course we're not going to have localization. So, it's actually a question for 40 n equals 1 if you could have localization, because there is localization with 40 n equals 1, but only for certain quantities. Like you can use to compute indices, but people don't know how to compute sphere partition functions. But I don't know if there's a proof that you can. I think no one's been able to figure out how to do it. So if you could, then that'd be very powerful, because then that'd be much closer to confining theories, because you have all kinds of confining theories with 40 n equals 1. Okay, so another general direction is studying irrational CFTs. So I didn't talk so much about 2D, because in 2D, a lot was already known. But most of the things that are known in 2D are about rational CFTs. Minimal models is the classic example. So minimal models you can solve completely, and many other rational CFTs you can also study. But a generic CFT, even in 2 dimensions, is irrational. It means its scaling dimension is an irrational value. And these CFTs, in principle, are just like higher dimensional CFTs, in that they're strongly coupled and we know nothing about them. In fact, even the existence for rational CFTs is something we don't know that much about. So beyond looking at the compact scalar, to construct a rational CFT is, I understand, still partially an open problem. And so this would be something that'd be very nice to understand using Bootstrap. And so there's been some attempts to construct irrational CFTs by coupling various minimal models. There's a classic example of coupling the 3-state Potts model, also some recent work by these authors, but none of these theories have been successfully bootstrapped. So I think this is a big target for bootstrappers, and something which even an entry-level bootstrapper could attempt. Because you don't need supersymmetry, you don't need any kind of fancy methods, just do standard bootstrap in 2-dimension, put in some global symmetry, maybe make some inspired guesses about the spectrum, and maybe you could find some of these irrational CFTs.
So for the bootstrap in 2 dimensions, is there any input about Virasora, or just not work with global?
Well, you could do either. You could use Virasora blocks. It's just with Virasora blocks, we don't always know Virasora blocks. So we know Virasora blocks in the simplest context, but not in more interesting contexts. So there were some nice papers by Shai et al. Where they were studying 2D CFTs with supersymmetry, and there they had to compute the Virasora blocks. That's what allowed them to do their study. You can also do Bootstrap without Virasora symmetry. Although you might as well use all the symmetry you have.
Louisville theory, not Louisville.
I think there's an S in it.
Louisville.
Or is there an? Oh, maybe not. I don't know. Sorry. That always confused me. Well, maybe he was from Louisville, Kentucky. Okay. So another thing you can do in 2D, unlike higher dimensions, is that you can impose modularity. So it's the modular bootstrap, originally shown by Helium back in 2011 with some recent progress. And so it'd be nice to combine modular bootstrap with conformal bootstrap to really nail down irrational CFTs. This way you could also learn about pure gravity and 3D. It's also been a topic of a lot of work, although I would still say most of the big questions are still unanswered. So we still haven't been able to actually prove that pure ADS3 gravity exists or anything like that. Okay, so some general directions about CFTs also is for in higher dimension. So far all the bootstrap studies have been with D between 2 and 6. And so for supersymmetric CFTs, we know that they only exist between 2 and 6 because you don't have a superconformal algebra outside of that. But for non-supersymmetric theories, there could be interacting CFTs above 16. We just haven't found it. Now, it's unclear if you could even define a non-supersymmetric CFT in 5 and 6 dimensions. So forget about going to 7 dimensions. Does it even exist in 5 and 6? Maybe you need supersymmetry. So the closest you can get is you can take the critical line model, and it's almost unitary in 5D. So this was first proposed by Igor Klebanov et al. And in fact, there was a bootstrap study by me and these collaborators back in 2014, almost 10 years ago, where we showed that the bootstrap can actually find evidence for this theory. Now you might say, how could you find evidence? If it's a non-unitary theory and unitarity is an input to the bootstrap, what's going on? Well, unitarity is broken only very slightly. So in these theories, it's basically the OP coefficients are real up to exponentially small terms, which are complex. And so that's why the bootstrap works kind of approximately. But indeed, in later studies, it was shown that as you made the precision higher, the bootstrap would start having funny stuff, which shows that it starts breaking down. But still, it was kind of interesting that you could kind of see these approximately unitary theories in 5D. but these aren't like proper unitary CFTs. Now, an easy reason to see why they don't exist as proper CFTs is that their Lagrangian would be a phi cubed theory, and phi cubed obviously is unstable. And so this is why you expect to get non-unitariness, which is exponentially small.
This is because basically one can write a theory with some high derivatives, which would be power counting and normalizable in high dimensions of ghosts, of course. But then that would be the way to construct quickly couple examples of.
You think, but that would be something like non-local theory, the stress tensor.
No, not non-local, but just add like a kinetic term, not d phi squared, but box phi squared.
Sure, but if we did that, that wouldn't violate.
Well, it would be non-unitary. It would be ghost in this theory, right?
Okay, yes. So I mean, look,
Right,
if you get rid of unitarity, then all kinds of things can happen.
Right. No,
Yeah, so
that's just a comment that it looks like constructing non-unitary CFTs
is not as interesting. Yeah,
and it should be rather straightforward.
non-unitary is not as interesting. What's interesting about the ON model is that it was like almost unitary. Is that it was like, it was a conventional Lagrangian, and just the lack of unitarity was due to like these really small terms. But I agree that like generic non-unitary theories, I'd say who cares. Recently, there was actually a paper by Voth et al., which was claiming to maybe construct a 5D non-supersymmetric theory. I think the way they did this is they started with some supersymmetric theory in 5D, and they did some kind of deformation. So I mean, I don't know whether this is believable, but at least there's some proposals. And these are all things one could try to bootstrap. You could take their proposal, put it in the global symmetry, and just see if you can get an island which matches their predictions. I suspect the stress tensor bootstrap will be a key thing to understanding if these theories exist, because the stress tensor is the only operator which is guaranteed to exist in a local CFT in any dimension. So you should start with a thing which you know must be there. And so people have done the stress tensor bootstrap in 3D, but people have not done the stress tensor bootstrap in higher D. And so I think this is kind of an outstanding question to do stress tensor bootstrap in higher D. It just gets more complicated because there's more structures you have to write down, but it's certainly doable. Okay, so another future direction that's very important is higher twist operators. So recall that if you think that your theory is saturating the bootstrap bound, then you can read off all the data in that 4-point function, the entire spectrum. But in practice, numerically, you can only so far read off low twist operators. We showed that example for the icing model. High twist operators, though, are essential to understand many physical questions. So for instance, there's this eigenstate thermalization hypothesis, which said the averages of high twist operators should have approximately thermal density matrices. Also in holographic CFTs, we discussed how high twist operators would rule to black hole states. So there's clearly a lot of motivation for understanding high twist operators. And so that's why I think this is the most important general problem in the bootstrap. It sounds very technical, but it's actually extremely important because you can answer all kinds of interesting physical questions if you can resolve this issue, which is basically how can you improve numerical bootstrap such that you can accurately get high twist operators. Now, it might be the answer is just brute force. Maybe if we just keep going to higher and higher precision using better and better algorithms, we'll just be able to get so many high twist operators that we'll have as many as we need. Maybe if we have the lowest 50 operators, then who cares about above the lowest? Or maybe we need a conceptually entirely different approach. Maybe there's just a completely different algorithm which somehow avoids this issue that in the conventional algorithm the tail of the distribution is exponentially small. Maybe in this other algorithm the tail is bigger, but nonetheless you can get bounds. Who knows? But regardless, I think this is a very big, both conceptual and technical question. Another big question is higher point functions. So all bootstrap studies for the most part have been about 4-point functions. There was actually a paper which came out just a couple months ago about 5-point functions by Dean Poland. Higher point functions in principle would impose new non-perturbative constraints. These higher point functions is an alternative way of probing high twist operators. Because instead of looking at a high twist operator for a 4-point function, it might be very hard to see. But if you look at a 10-point function, what used to be a high twist operator will now be kind of leading order at large n. So this would be another way of seeing high twist operators. So to do this higher point numerical bootstrap, you need many ingredients. First of all, you're now going to have multiple OP coefficients appearing, not just 2 OP coefficients. So you have to have some kind of algorithm that takes into account the fact that you have a product of multiple, real values, and their product is not guaranteed to be positive. And so instead, you'd have to have some kind of algorithm which involves positivity of tensors, where it's because you have multiple OP coefficients. Also, conformal blocks for higher point functions are not known in general, although there has been some progress in the last couple of years, but we don't have the most general solution. Nonetheless, though, I should say that there was a paper by David Poland where it was the first baby step towards doing numerical bootstrap for 5-point functions. Okay, so the bigger question is, what's the point of all this? This is something you should always ask whenever you hear talk, like why should I care? So we've discussed many examples of CFTs that have almost been solved numerically, as well as prospects of solving other CFTs. But what ultimately is the general lesson of computing all local CFT data, save for the icing model? So I understand the critical exponents that we measure experimentally, but why do I care about the 50th lowest dimension operator of spin 72? Similarly, what new things can actually be learned from a bootstrap solution of n equals 4 super mils? So I gave some answers. So for instance, for n equals 4 super mils, I said that you could study black hole states in the holographic CFT. But this is just one example. I mean, surely there's more we should be able to learn from a putative numerical solution n equals 4 super mils. I mean, like, I think it would be a criticism of us as theorists if we were given a solution n equals 4 super mils, and we're just like, oh, who cares? You know, it's like we should be able to think of interesting questions, you know, to use this answer for. So, I mean, the way I would say it is that I think we are on the brink of a revolution of new non-perturbative data, and we need new concepts of what to do with it. You know, so for all the people in the audience who are very conceptually minded, maybe they can start thinking, okay, say someone hands me the lowest 50 operators and n equals 4 super mils, you know, what predictions do I have for that? What can I learn from that, etc. So to conclude, the Bootstrap Manifesto, the Conformal Bootstrap program disdains to conceal its views and aims. It openly declares that its ends can be attained only by numerical solutions to all existing CFTs. Like perturbative methods tremble at a bootstrap revolution. Physicists have nothing to lose but their Lagrangians. They have a non-perturbative world to win. Working theorists of all disciplines, bootstrap. So this is a rewriting of the Communist Manifesto.
Do you want to do a statue of yourself now?
Not myself. Although I guess this is what those countries would do. They're always going to add in the next guy. You know? So you start with Lenin, and you have Marx.
Thank you.
All right. So yeah. So any questions? I guess in the remaining minute or two.
There was an idea that turbulence actually could become conformal by Pavlov.
Well, I think actually the defense is going to talk about turbulence.
Where did you talk? Maybe.
No, I didn't talk about it. But this defense they're having now, I think he's talking about turbulence.
No, but I meant to solve this use numerical bootstrap.
Possibly, yeah. I mean, if you could someone describe it as some conformal theory. Although, you know, I don't claim to understand it very deeply.
So are there ideas if you don't, like for gauge theories in 4D, if you don't have a large flavor symmetry, are you just shit out of luck, or is there?
You're saying a finite. You're saying if you don't have a large gauge symmetry. Well,
I guess you had this idea about the inputting NC through the anomaly.
Yeah.
Yes,
So,
what is
okay. So when you have supersymmetry, you have localization of other methods. Without supersymmetry,
Yes.
you need to put in the number of colors. In 4D, I think you could put in this anomaly. I think that would be one path forward. In 3D, you have multiple operators, which are sensitive to the number of colors. And that's why we've already had some progress for 3D gauge theories. But yeah, I mean, for 4D gauge theory, I think it's kind of the big question, very unexplored. So I think it's like a good target for people who are interested.
And are all like, would these all be IR CFTs, or also could there be like strongly coupled UV fixed points for these?
Well, I mean, we're just talking about CFTs in general. I mean, like whether or not it's IR or UV doesn't really matter. I mean, like, I mean, people sometimes use the word UV CFT in 5 dimensions because in some sense you're kind of flowing back. But like, I think, you know, the most conceptual best way of talking about it is that it's always matters.
More questions? If no, let's thank Shai for a nice lecture course.